Temperature as a concept. Now, we think more about temperature when we're cooking meat, or if you don't, you should. Or we think about the human body is supposed to be like 98.6 degrees, and if we are above or below that, we might have some health issues. But when you think about temperature in chemistry class, you need to be thinking of kinetic energy. Okay, so kinetic energy, and you'll use this again next year in physics class. Kinetic energy is one half of the mass of any particle or object, and in this case, we're going to be talking about molecules of gases, or atoms of gases in the case of like the noble gases. So the molecular mass times the velocity and how fast they're moving. Okay, so here's what you need to grasp about temperature. Temperature is just a measure of the average kinetic energy of a sample of a gas in this case, because we are talking mainly about gases, but it also works for solids and liquids. So if we would take a sample of a solid, a liquid, or a gas, not all the particles will have the same kinetic energy. Some will have a higher kinetic energy, some will have a lower kinetic energy, and some will actually have the kinetic energy that matches up directly with that temperature. But when you take the average, that's a temperature. Okay, so a sample at 100 degrees Celsius of a gas will have the same average kinetic energy as a sample of a solid at 100 degrees Celsius. Okay, so those will have the same average kinetic energy, just one's a solid and one's a gas, And, why one's a solid and one's a gas, that all depends on bonding and other things. But so far as temperature goes, as long as you have a temperature, you have that same average kinetic energy. Okay? Now, mass of the particle, that could indicate speed. If you have a smaller mass, to get to a certain temperature, you're going to have to move faster. Because when you look at the formula, you multiply the mass times the volume squared. And so if you have a smaller mass and you want to be at the same temperature, so for example, if you take like hydrogen, which has a mass of, 2, and oxygen, which has a mass of 32, if they're both at the same temperature, the hydrogen is moving much faster because it has less mass in here to multiply in. The oxygen is going to be moving slower because it's more massive. And, that kind of follows. If you would use a sports analogy, when you're playing American football, the big linemen, they have more mass, but they move slower than like a wide receiver, which has less mass but moves faster. It's kind of how you look at that analogy. And so we talk about a Boltzmann distribution. And so say we have a sample of a gas at like 100 degrees. Okay, we're going to get an area under the curve that looks like this. You have some here that are back here. You have some that are sort of outliers up here. They have more kinetic energy, and but then when we take the average, like kind of like a grade, the sample is right there. Now let's call that 300 Kelvin. Okay, so let's call this 300 Kelvin. So when you have 300 Kelvin, that's what your distribution looks like. Now, if the temperature increases, I want you to think about that curve as a piece of string. And so if that temperature increases, we're just going to pull that string a little bit up this way. And the area, when you're doing these curves, the area under the curve should kind of look the same. So you have, because you're going to have the same amount, so you don't like drag it out way out here, but this would be like, not 100, 1,000. Okay. And so when you get 1,000 K, what you have is you end up with a higher overall temperature, and you just have a wider distribution. The highs are higher, the lows are still basically the same, but you have more options here, and therefore that's what goes and gives you the higher average, because you have more particles with more energy at a higher temperature, and so it gives you the higher average. And if we were going to cool it down, you would just push that string back, and it would. Heck, let's do it. And it would look like that. Okay, and so the more temperature, the more kinetic energy, and the more possibilities of higher kinetic energies. And therefore, that's why the curve keeps sort of widening out as we go. So that's temperature as it applies to gas laws, Boltzmann constant, or Boltzmann distribution, and a graph. Have a good day.